Okay, well, thank you very much once again for the organizers, and thank you very much. This is our second lecture, and I'm going to speak, kind of continue from yesterday and speak with kind of a motivation for the work that I talked about yesterday, or an application, if you will, of the work that I talked about yesterday. And again, I'll speak in more general terms, and Mahesh will continue with details of the proofs. Okay, so so I want to start by talking about Hilbert's 12th problem. So let F be a number field, and we want to understand the maximal abelian extension FAB. So classically, so it's, what does one mean by classically? But I'll just say that it's known how to do this for F equals Q, and when F is a quadratic imaginary field. So Q adjoin root negative D, where D is a positive integer. And Hilbert asked, and I'll give some quotes from the statement of his 12th problem in a moment, but Hilbert asked for the generation of FAB using the special values or transformation properties of complex analytic functions depending on F. And so we have approached to the question of the construction of FAB using p-adic analytic functions. And I'm going to describe that formula today. So how does this question compare with what one knows as class field theory? So class field theory does not describe the field FAB, but it does describe the automorphism group. So it does describe, the Galois group of FAB over F. Okay, so let me say a little bit more about that. So what do we know from class field theory? So we know that for every positive integer n, there's a field extension, which I'll denote by Fn, which is called the narrow array class field of conductor n. And these have nice properties of sort of how you organize them. So Fn is contained in Fm if n divides m. Fab is obtained by the union of these Fn. So these are all finite abelian extensions of F, okay? And Fab is their union inside some safe fixed algebraic closure. And then we have an explicit description of the Galois group of Fn over F. And so I'm not going to write what that is in general. In general, it's some generalized class group. When n is 1, it really is the class group, the narrow class group, which are in here as the narrow Picard group. And the Galois group of Fn over F1, it's very easy to describe. It's sort of OF mod n star mod the group of totally positive. You're the image inside OF mod n of the group of totally positive units of F. So a simple example of this is when F is Q, then the Fn in that case, the Qn, is just the nth cyclotomic field, Q adjoin e to the 2 pi I over n, and the Galois group of Qn over Q. So Q1 is just Q itself, and the Galois group of Qn over Q is Z mod n Z star. So in this case, there's no totally positive units, right? The units is 0 plus or minus 1, the totally positive unit is just 1. So this extra quotient you have to take does nothing. So this is what class field theory tells you. In general and in the specific case of Q. Okay, now, as I just described, class field theory tells you the Galois group of Fab over F, okay, or equivalently the Galois group of each of these Fn's over F. And you can describe this as some quotient of the idels of F. And we'll kind of discuss that a little bit later. But the goal of explicit class field theory is to construct the field Fab itself rather than just to describe its Galois group. That is, so we want to describe or equivalently each of the fields Fn using analytic functions depending only on the ground field F. So if you go back to the case of Q, we kind of know how to do this. QAB is obtained from Q by adjoining the special values of the analytic function e to the 2 pi I over x. And in fact, the special values you adjoin are the values at all the points of the field itself. So the field is Q, you evaluate this analytic function e to the 2 pi ix at Q, and you adjoin the values of the special values of that function, of this complex analytic function, this holomorphic function, you adjoin the special values and you get the field QAB. Okay, and there's just kind of a similar description when the ground field is a quadratic imaginary field. So suppose that F is Q adjoin root negative D for a positive integer D. Then you consider an elliptic curve with complex multiplication by the ring of integers in that quadratic imaginary field, and you adjoin the J invariant of that elliptic curve together with essentially the end torsion points, the coordinates of the end torsion points of that elliptic curve, then that gives you the field Fn. This is now slightly off, and there's something called a Weber function, which provides sort of a modification of this, which gives you the correct answer. But the punchline here is that modular functions play the role of the exponential function in this setting. So here the j function is the usual j function, a modular function. And so in general, these Weber functions apply to the coordinates of the end torsion points of this. This can be thought of as certain special modular functions that you're applying again to points in the upper half plane that live in the field F. Okay, so if you want to think of this as special values of functions, you can again think of this as special values of certain modular functions. All right, so this is kind of the prototype for what one wants to do. And so Hilbert, in his famed ICM address of 1900, when he stated 23 problems that have motivated us for over a century, and right in the middle as his 12th problem, he discussed the question of the explicit generation of class fields. So he starts with a description of the Kronecker-Weber theorem, the theorem that every abelian number field arises from the realm of rational numbers by the composition of fields of roots of unity is due to Kronecker. He continues with a discussion of the quadratic imaginary case, which at that point had not been completely tied up with a bow. It was largely known, but not completely stated in the form that I gave. So he says, okay, let's finish off this case. Since the realm of the imaginary quadratic number fields is the simplest after the realm of rational numbers, the problem arises to extend Kronecker's theorem to this case. But then finally, the extension of Kronecker's theorem to the case that in the place of the realm of rational numbers over the imaginary quadratic field, any algebraic field, whatever is laid down as the realm of rationality, seems to me of the greatest importance. I regard this problem as one of the most profound and far-reaching in the theory of numbers and of functions. So Hilbert sees already that the case of generalizing from quadratic imaginary fields to general number fields will require some conceptual leap, that this is a far more significant problem. And I should say I've been selective with these quotes. That is, there's more that Hilbert says in his problem, where he talks more specifically about taking complex analytic functions with special transformation properties and applying them to values in the field itself, which you should be able to make sense of as the domain of your functions. And he's looking for something that's very closely modeled after the two cases that I've just described, Q and quadratic imaginary fields. And this is the prototype for what Hilbert expects to be the solution to the question of explicit class field theory. Okay, so now I want to go back to the setting that I described in the previous lecture, and this slide I think is just taken directly from that lecture. So the setup that I'll consider is that where your F is a totally real field. Okay, and I want to consider the Brumer-Stark conjecture again, or I'll remind you what it states in the next slide. So for that, we consider a finite Galois extension of F, whose Galois group is abelian, and I assume that abelian extension is a CM field. And we let S be the set of infinite places and ramified places, and T to be some other finite set of places disjoint from S, satisfying some mild conditions. We have this S depleted T smoothed L function. So it's just the usual L function of a character chi of G, kind of with the Euler products at primes and S removed and smoothed in this way by multiplying by this Euler-like product at the primes in T. Okay. And I'm just going to remind you here that the Brumer-Stark conjecture. So we take a prime ideal of F that splits completely in H, and we consider the group of P units that have complex absolute value 1 at every complex place, and such that U is congruent to 1 modulo every prime ideal of H lying above those in this set T that I've taken. And the Brumer-Stark conjecture is that if I fix a prime ideal of H above P, then there exists a unit in UT minus a P unit, such that for every chi evaluating taking the valuation of this unit, all the primes above this Gothic capital P and taking the corresponding linear combination given by the values of the character chi, that should give me the L function of each character chi. So this should hold for every character chi of G. Here's the Brumer-Stark conjecture, and we've kind of proven this away from 2. So we've proven that there exists an element U and UT minus tensor to the Z bracket 1/2, satisfying this property. And now for today's lecture, the goal is to describe the applications of this result or generalizations of our result to Hilbert's problem, or to the question of explicit generation of class fields. Okay, so in this direction, we want to say, what is the extension? What is the field generated by the Brumer-Stark units? So if H is a cyclic CM extension of F in which P splits completely, then you can show that the Brumer-Stark unit for H, if it exists, generates H. Okay, generates the field H. And since the cyclic extensions of an extension generate the field, you can basically get all CM extensions of F this way, and CM abelian extensions of F in this way. And if you want to go beyond the CM case and get fields of arbitrary signature, then you just have to join some square roots to make sure you don't have a totally complex. You don't have a field that only has that's only a CM field. So you take any elements whose signs give you all possible signs. So there's n real embeddings, and so any element of F has n signs associated with it. And if you take any elements that generate, the F2 vector space of signs, all possible signs, and you take their square roots and you adjoin them to F, then once you have that and you adjoin all this Brumer-Stark units, then you've obtained sort of the maximal abelian extension of F. So that's a theorem, so we describe this as sort of elementary, but it's described in our paper. And I'll just mention that one has to vary P here, because the condition on P is that P splits completely in your extension. And of course, you can't take one P that splits completely in every extension. So given kind of an Fn that you want to construct, this is the narrow array class field of conductor n, you have to kind of start with a P that's maybe congruent to 1 mod n, and therefore it's sort of splits completely in that extension. So that's so that's one artifact of our construction of these abelian extensions, is that you have to do sort of p-adic analysis for varying primes P if you want to get the maximal abelian extension. So for a fixed prime P, what you most naturally get from this perspective of Stark, sort of the maximal abelian extension in which P splits completely. See, when you're doing things in a complex analytic sense, in an Archimedean sense, you don't have to worry about this, because the complex place will always split completely. So, all right. All right, now I'll remind you. So,
is the proof based on class field theory or something more delicate?
This is elementary, yeah. So it's based on class field theory. Yeah, there's nothing delicate involved in that previous theorem. Okay. So yeah. So let me just remind you. So the alternate perspective on the statement of the Brumer-Stark conjecture that we gave, there was this STICKELBERGER element, we called it. It's an element of the integral group ring Z bracket G that interpolates the L value. So it's the unique element in C bracket G such that chi of theta is equal to the L function that you're interested in. And the theorem of Deligne, Ribet, and Castunugos is that element lives in the subring Z bracket G, integral group ring. Okay, and what I want to state now is a conjecture of Gross that refines the Brumer-Stark conjecture by stating, essentially, you can view it as stating some congruences that your unit has to satisfy. Okay, those congruences come from class field theory. Okay, and it's stated in terms of the STICKELBERGER element theta. Okay, so this is Gross's tower of fields conjecture. So we're going to consider an auxiliary abelian extension of F, which I'll call L, and we, it contains the one that you start with, and it has to have control over its ramifications. So we assume that L is unramified outside the same set of primes that contained all the ramified primes of H, except now you allow yourself one additional bit of ramification, which is you allow ramification at P, the prime was split completely in H. So just to make a little diagram, here's F. You had your H that you started with. This is what's called tower fields. You have this L that's sitting above it. And again, P has to split completely here, but it's allowed to ramify. Okay, so ramification allowed. At P is allowed. Okay, and that's the only difference, but there's no ramification outside your original set S, where the ramification of F occurred, of H occurred, and this P. Okay, and now we have some, some notation. So your original Galois group was G, and I'm going to call this gamma, and I'm going to call this Galois group kind of math frac G. Okay, so this Gothic G modulo gamma is isomorphic to the original capital G that I started with. Now there's an augmentation map, which I'm going to call epsilon, from the group ring of Gothic G to the group ring of regular G, of course, right? Regular G is a quotient, so there's a natural map from this G to this G, so you just reduce, and that induces a ring homomorphism on the group rings. Okay, we're just going to call that epsilon. It's called some relative augmentation map, this is called. And if you look, so now I have to sort of, since everything is a little bit more subtle, I was just calling it theta before, but I have to be very careful about the smoothing and depletion sets and which field I'm looking at. So my thetas are going to get adorned with a lot more information that I've been suppressing. So if I look at the SPT, right? So SP is the sort of the minimal set that you can take when I talk about the theta of L over F, because the smoothing set has to contain all the ramified places, and S is precisely the set of places. SP is precisely the set of places that L is allowed to be ramified. So I have to I have to take SP here, and I just take the same smoothing set. Then what happens if I look at the image of this under the augmentation map? Okay, well, by the kind of functorial properties of L functions, it's very easy to check. You just basically look at the definitions that the augmentation of theta spt of L over F is just the theta spt of H over F. Okay, but now H of F doesn't require SP as my smoothing set for theta. I'm allowed to take just theta sub st, because H is ramified only at the primes in S. There's no ramification at P. And in fact, if you see the relationship between theta sp and theta s, what it is you're just removing an Euler factor. That's the definition of what the smoothing is. You remove the Euler factors at that prime. So what is the Euler factor at P? It's just 1 minus, these are sort of theta, L values at 0. So there's no norm of P to the minus S. Norm of P to the minus S is just 1. So it's just 1 minus sigma P, the Frobenius at P. Okay, so that this first equality is just by definition, going from here to here, that, what is the definition of this smoothing set? It's just removing Euler factor. So this is the definition. But now you see my assumption is that P splits completely in the extension H. So P splits completely here, which is to say that its Frobenius is trivial. Okay, so this sigma P is equal to 1. So 1 minus sigma P, this is 0. Okay, so this is what's called a trivial zero phenomenon. There's a trivial zero. It's because you removed an Euler factor that is 0. So the punchline is that this theta spt of L over F lives in the kernel of the relative augmentation map epsilon. So theta lives in the kernel of epsilon. So this is all just the setup for Gross's conjecture. So now I can state Gross's conjecture. which is I have this theta SPT. This is of L over F. Okay, I've kind of suppressed that. Kind of start suppressing things as soon as I'm able. So this is of L over F. It should probably be more explicit here. Okay. That this is now in the kernel of the relative augmentation map. Okay, so I call that kernel I. And Gross's conjecture is a congruence for this theta in I mod I squared. Okay, so one wants to think of this as a kind of a formal derivative, that this is an integral way of thinking of a derivative. If I have, from algebraic geometry, this perspective is that the ideal of a ring, if you think of elements of the ring as functions on the spec of that ring, then an ideal of a ring is sort of modding out by an ideal, looking at the value and the quotient is sort of taking the value of a function at the point corresponding to that ideal. So, so somehow saying that this element theta lives in I is to say that the function represented by theta vanishes at the point represented by I. And if that's the case, well, what's the derivative of that function? It's the image in the I mod I squared. So this is kind of a formal way of taking a derivative. And that was just sort of some conceptual, intuitive mumbo jumbo, but I mean, you can just do this purely algebraically if you want, but this is sort of the motivation or the intuition for Gross's conjecture, that this is a derivative. And the other side is some sort of algebraic way of thinking about a logarithm. So this is kind of a standard yoga and Stark's conjectures that you want to compare a derivative of an L function to a logarithm of a unit. So I've kind of explained in some intuitive way why the right-hand side, the image of theta and I mod I squared, is the derivative of an L function, and the left side is Gross's version of the logarithm of the unit. So you take the unit, or in this case, all of its conjugates, the sigma of UP, a sigma ranges over the Galois group, and you take its image under the local reciprocity map. So if you consider this gamma is the Galois group of a finite abelian extension of H, so it can be viewed as a quotient of the adels of H, and of course the local component of the adels at the prime P that you've chosen is just HP star. So you can consider this composition is just a local art and reciprocity map. Okay, viewing the sort of decomposition group at this prime P as a subgroup of this gamma. Then Gross's conjecture is you take the image of this. Okay, now if I take the image of your unit, or any of its conjugates, then this is an element of gamma. So if I take that minus 1, then this is an element of I, kind of by definition. Right? Anything in gamma minus 1 is in I. It's in the kernel of epsilon, the augmentation map. Anything gamma goes to 1 under the augmentation. So this is an I. And so you take this linear combination, and this is sort of like taking the chi twisted linear combination when there's no chi. So if you're doing it as a group ring element, so you're putting it all together for all chi's, then you take the sum over all sigma and G, and you kind of weight this element by the sigma. And sigma tilde means any lift to G of sigma. So sigma tilde, any lift of sigma to this Galois group, okay? And it doesn't, this expression on the left side, its image in I mod I squared doesn't depend on the lift that you've chosen, right? Because any two sigma twiddles that you choose will differ by element of gamma. And then that will be, how will that change this? Well, that will then be an element of I times sort of an element of I squared, right? So then the difference will be something in gamma, something in gamma minus 1 will be the difference will be something in I. So then you'll have something in I times something in I squared. So it's easy to check that changing your lift changes this expression by something in I squared. So the left-hand side is well defined in I mod I squared. Okay, and Gross conjectures that these are congruent. Okay, so this is some algebraic some integral algebraic way of thinking about a Stark's conjecture that sort of the derivative of an L function should be equal to the logarithm of a unit. This is a very nice, purely algebraic way without actually talking about analytic derivatives in any real sense. Okay. So what is this saying? So let's try to unwrap this a little bit. Okay. So what is I mod I squared? So for those of you thought about, Maser-Tate type conjectures, or, this conjecture of Gross before, then this I mod I squared is a very familiar thing that comes up. You can say that exactly what I mod I squared is isomorphic to is just the group ring of G tensored with gamma. Okay. So an element of this I mod I squared is just a bunch of elements of gamma indexed by the group ring. Okay. And right, so this gamma, as I said, it's the Galois group of an abelian extension of H. So it can be viewed as a quotient of the adels of H, and I'll just write that quotient as JL, whatever that is the kernel of the global art reciprocity map from AH star to gamma. I'm just defining that to be JH. So this kind of equality is by definition. Okay. And so Gross's formula, if you look at the formula I just gave, it's a formula for basically all the conjugates of U. If I view them in this, inside this, this unit, if I view it as an element of the adels, where I kind of only look at its local embedding at P. So I embed this element. This is some global algebraic element of H. How am I viewing it as an adel? I put sort of ones everywhere, and then I put, one. So ones everywhere except in the component, the local component P. If you look back at how I defined it, I used just the local art and reciprocity map at that prime P. Then it's sort of giving me a formula for sigma of UP here. Okay. But up to some fact that I'm quotienting by something. I don't have all of AH star here. I have some quotient of it. Okay. So you want to say, okay, what's the maximal information I can get from this? So let me replace L. Sort of, if I take the maximal L I can take. So the maximal L you could take is the maximal abelian extension of F that contains H, and that's unramified outside S and P, right? And if you call that L sub SP, then you get a formula sort of in the Galois group of that extension. And you call that J. What is that? Well, class field theory tells you exactly what that J is, or what that Galois group is of the maximal abelian extension of F containing H that's unramified outside S and P. And if you check what that is, that can be written down explicitly as a certain quotient, okay, of just the product of FV star as V ranges over the places in SP by some group of units, or the topological closure of some group of units. So EP of HS, this is the group of totally positive units Sorry, I think this might be there's a typo. This should probably be of FS somehow. To double check this, I think it's totally positive units of F, congruent, totally positive. First of all, P units, totally positive. I have to. This is important. Totally positive P units. A little confused by the H here. I think it should be P of F. Congruent to 1 mod primes in S. Okay, and so that's the group on which Gross's formula, if you look at the sort of union of Gross's formula over all possible Abelian extensions L that I'm allowed to plug in to the conjecture, it's giving me a formula for UP11111 in this sort of finite product, but sort of modulo this quotient. That's the issue, is that you're having to mod out by the topological closure of this group of units, and this group of units can be really big. It can kind of eat up this space. So what one wants to do is get rid of this thing that you're modding out by. Okay, so I want to find a refinement of Gross's conjecture where I'm not modding out by anything, and I have a formula for UP sort of in FP star. So that's maybe I'll say the goal. Oops. Sorry, there's a problem with the iPad where the bar is okay. So let me write the goal here. So the goal is find formula for UP and all its conjugates in, say, FP star rather than a quotient, which is what Gross's formula gives. So I want a refinement of Gross's formula that does this. Okay, and so to do that, I'm going to use some ideas of Shintani. All right, so I'm going to talk about Shintani's method now. Okay, so this is kind of cluttering the screen, so I apologize. I'll delete this. Hopefully people got that. What the goal is, it's to define a formula, an analytic formula for UP in FP star rather than this quotient. Okay, so now to do this, I'm going to remind you Shintani's method. So let E of n denote the group of totally positive units that are congruent to 1 modulo n. And Shintani's theorem is that there exists a assigned fundamental domain for the action of this En on the totally positive orthant, consisting of simplicial cones generated by elements of F. So I'm thinking of F as embedded inside R to the n, right? So n is the degree of F. So F is a totally real field of degree n. You could embed it in R to the n just by choosing some ordering of the n real embeddings of F. And so F sort of sits inside there, and OF is a lattice inside R to the n. And you can think of, F star is acting on R to the n by sort of component-wise multiplication. So once I've embedded F into R to the n, then an element of F acts on R to the n by multiplication component-wise on vectors. So that gives me an action of F star on R to the n, and you can ask for a fundamental domain for the action of the totally positive units on the totally positive orthant. Okay, so a nice picture to keep in mind is the real quadratic case. This is sort of the case where you can see really clearly what's going on, which is in that case, sort of, you could just have R squared, and the totally positive orthant is just this totally positive quadrant here. And you can give a fundamental domain just by sort of taking the vector 1, right? So this is, 1 is embedded as 1, 1. And then if I take a generator for epsilon, so E of n, in this case, E of n is just cyclic generated by some epsilon, right? So the group of units in a real quadratic field, totally positive units, is cyclic. That's one way to Z. And so that will be embedded in terms of the two real embeddings as sort of, an epsilon and epsilon inverse. And then this will be a fundamental domain. So to be really precise, you have to take the interior, and then you have to take sort of one of the boundary cones, right? So the fundamental domain will be, right? So the fundamental domain will be the union. So I'll just say C0 plus C1, where this is the ray, and this is just the interior. The interior, okay? So you take one of the boundary faces or boundary rays and the interior. So this is, exactly what it is in the case of a real quadratic field. In the case of a general number field, okay, or a general totally real field is the only setting I'm considering here. Oops, accidentally stopped that. In the case of a general totally real field, Shintani proved that there exists a fundamental domain, but didn't write down a formula for what it is. And the reason that I've allowed myself signs in this theorem is that because it's actually nicer, simpler to write down an exact formula in terms of a generating set of this E of n, in terms of a basis of E of n, it's easier to write down a sign of fundamental domains if you allow yourself sort of plus one cone minus another cone plus another cone. If you allow pluses and minuses, then or general integer coefficients, then it's easy to write, not easy, but one can write down an explicit formula for what this domain looks like. So computationally, this is very nice because then you don't have to worry about writing down a specific fundamental domain, which is a union of simplicial cones where all the coefficients are positive or where all the coefficients are just 0 or 1. That's sort of Shintani's theorem that such a thing exists. That's a little bit harder to do computationally. But with this construction, it's totally fine if you use signed codes. Okay, so what do you do once you have this fundamental domain? The point is that somehow the partial zeta function associated to an ideal can be written down as a sum of 1 over norm of alpha to the s, as alpha runs over the elements in an ideal inside of a cone, right? This is kind of Shintani's decomposition of the zeta function of a number field. Okay, so if you sum, okay, to make things more precise, you take an element in the inverse of your ideal that is congruent to 1 modulo your n, and you sum over all alphas in B n inverse plus Z, then if you sum over all the elements in a cone that are sort of inside this translate of your lattice of 1 over norm of alpha to the s, and this basically, and you look at the value at 0, this is basically the value of a partial zeta function. Now you can refine that by taking congruence conditions. So you can take a compact open set U of say OP. So OP is this is the completion of OF at P. Okay, then you can sort of restrict your sum to only some alpha satisfying some congruence conditions at P. Then this is what's called a Shintani zeta function. So Shintani studied these zeta functions and proved their analytic continuation and studied their special values at 0. And an interesting thing is that if you take a certain linear combination of 2 of these, so this is the t-smoothing done explicitly in the Shintani context. So you take sort of one zeta function and you subtract off the value of another one where it's kind of weighted by the norm. So this L is the norm of my sort of Gothic L. Don't know how to indicate that. They kind of draw them both the same way, but this L is the norm of this cell. Okay, then you take this linear combination, then you can prove that you actually get an honest integer. Okay, so this is an honest integer. It lives in Z. Okay, and in this way I get a measure on OP. Okay, so if I refine an open set U into a V and a W, and I sort of partition it into a V and a W, and then the mu of U is equal to the mu of V plus the mu of W. That's sort of obvious just because it's a sum of things in U. So if I partition U into V and W, then that's just the sum of what I get from taking V and taking W separately. So this kind of amazing is that this is integer. Usually if you have something that satisfies this kind of distribution property where something gets broken up into two, if something is a disjoint union of two sets, then the value is the sum, then somehow you think you need to introduce denominators to get that to hold, because you're kind of dividing something into two pieces. You think that as you get smaller and smaller, that you'd always have to sort of you'd have to get denominators eventually. But what's amazing is that somehow these are integral for all compact open sets U. Okay, this is a very nice fact that comes out of Shintani's formula. Okay, so now once I have that measure, so I'm kind of implicitly here doing the special case where P is an inert prime, so it simplifies the notation a little bit. So I assume that P is generated by a rational prime P. Then the conjecture, my conjecture for what UP is, so this is a refinement of Gross's conjecture. So remember, Gross's conjecture tells you what UP is in some quotient of FP star, or more precisely, UP comma 11111 in FP star cross, the local completions at all the places in S, modulo some big quotient where you're modding out by some topological closure of a P unit group. And my conjecture is to give you an exact formula for UP, at the place at P, the completion at P, without any quotient. And so what we're going to do is just multiplicatively integrate the function X with respect to the Z-valued measure. So this is, how is this defined? This is just defined as a limit of Riemann products. Okay, so maybe I can just say that. So this is the limit. So this integral part, if I take out the power of P, this is the limit as n goes to infinity of, well, you take the product over all A in OP mod, so P to the n star, and you just take A to the power of mu of, A plus P to the n OP. Right, so this is, if it was a sum instead of a product there, and I was multiplying instead of exponentiating, that would be a usual Riemann sum, right? You take your point in your open set A, you weight it, and you multiply it by the measure of the corresponding open set A plus P to the n OP, and you take that Riemann sum, and then you take the limit as your your refinement of this open set OP into smaller and smaller open sets, I guess finer and finer. And you take that limit. That's how you define an integral. It's a limit of Riemann sums. So the only difference, this X to the integral sign just says you take Riemann products rather than Riemann sums. And for this, now you see why it's very nice that these are integers. So it makes sense to take A to the power of mu, because that's just an integer. So you can compute that. So that's the conjecture, that's the refinement. And so that gives an explicit sort of analytic formula for the Brumer-Stark unit. So it gives an p-adic integral formula for these Brumer-Stark units that I told you, for all intents and purposes, together generate the maximum abelian extension of F. Okay, so just some simple square roots, and those guys generate the maximum abelian extension of F. And we've now given a formula for them. And the theorem with Mahesh is that this formula is correct under some mild assumptions. So if you assume that your Gothic prime P lives above a rational prime that does not ramify enough, so if you just have to sort of avoid ramification, then the conjectural exact formula holds up to a root of unity in FP star. And I'll just mention that recently a student of Mahesh's, Matthew Honor, has removed this root of unity. This root of unity, other than two power roots of unity. Two power stuff is always difficult. So we basically have this exact formula, as long as you kind of exclude finally many primes, the primes above those that ramify in F. Okay, and I should mention that through a completely different method, Darman, Pazzi, and Vonk have obtained the same result in the case that F is real quadratic, P is inert prime. So in kind of a special case, using completely different methods, they've obtained essentially the same result. Okay, yeah, I mean the result is a little bit more specialized. They kind of only work with the Hilbert class field rather than an arbitrary CM abelian extension, but probably it can be generalized to the general case. Okay. Okay, and I just want to mention that these integrals are actually computable, explicitly computable. It takes a little bit of work. I mean, one doesn't usually use the actual definition that I gave as a limit of Riemann products. You kind of you have to prove formulas for the moments of these measures, and you want to compute the integral in an intelligent way by expanding the function x sort of as a power series. That you take the logarithm and you expand the log of x as a power series, and then you compute the moments and you expand the integral that way. That's much more computationally efficient than just using the formal definition as a Riemann product, because every refinement you get, p to the n, you exponentiate the number of terms you'd have to do in the sum. But anyway, so there's some math to do in computing this, but it's possible, and you can actually do it on a computer. It's very nice. So you ask the computer to compute this integral and all of its conjugates, and then once you have it, you compute the elementary symmetric polynomials of these elements that you computed, and you expect these to be algebraic integers in F. And you ask the computer, okay, so this is some crazy p-adic number, but it's supposed to be, an integer, half an integer. What is it? The computer will tell you, okay, 9 halves. And you've done something to like 100 p-adic digits and you get like 9 halves, then you know that it's going to be right. So you write down this polynomial, and then you check after the fact that indeed the splitting field of this polynomial over F is an abelian extension of F that's sort of, in this case, we're only looking at, the narrow Hilbert class field. So this is what I would have called F1 in my previous notation, the narrow Hilbert class field of F. And indeed, you get an everywhere unramified abelian extension of F of the correct degree is a cyclic extension of degree 4. Then it's you've sort of proven that it's the narrow Hilbert class field. So, and we never fed it the answer, right? We never told the computer what the narrow Hilbert class field of this field F is. We just told F is, Q joined square root of 305. The D, by the way, inside this red box, that's 305. I just simplified it by writing D. So we never told the computer anything other than D. So we just told it Q join root 305. We told it take your prime P to be 3 and compute the narrow Hilbert class field, and it spits out this polynomial by calculating this p-adic formula that I gave you. And so it's very nice. So we're showing that this sort of solution to the question of explicit class field theory, it's not just conceptual, it's not just theoretical. This is actually practical. You can use this to compute the Hilbert class fields of totally real fields and general Ray class fields of totally real fields. So I'll do a bigger example. 473 has a property that its narrow Hilbert class field is cyclic of degree 6, and you can kind of compute the units, and you get this nice degree 6 extension, which after the fact, again, you can check indeed generates an abelian extension of F that's cyclic of degree 6 and everywhere unramified. Okay, so I should mention I had 2 students at Duke, Yijia Liu and Max Fleischer, 2 undergraduate students who did the coding for this and wrote the programs, and they generated tables with thousands of examples of generating these class fields with these polynomials, and it's all on GitHub. You can look up these nice formulas. Okay, so now let me end with a summary of a whirlwind kind of summary of the proof, and I hope Mahesh will give details of this in his lecture. So how does this work? So recall that Gross's Tower of Fields conjecture states that I have a congruence for the vector UP11111 to some STICKELBERGER element in some quotient in FV of this product of FV stars. And it's going to turn out that kind of these extra ones are playing an important role for us. Okay, and this is the Galois group of kind of the maximum abelian extension you can take over H. Okay, and so here's our first lemma, which is that if you write VP for a conjectural analytic formula for UP, you want to sort of show these are equal, right? Then the first step is that this is consistent with Gross's formula, that VP1111 is congruent to theta in this quotient, okay? And basically, this is not too deep. There's 2 aspects of this, okay? So the first of all is that you can write down some analytic element here, okay? And why is it equivalent? So some analytic element that depends on P and S, and why is it equivalent to theta in this quotient? That is, why is it consistent with Gross's formula? Well, once you mod out by units, then kind of Shintani's formula is just asking why Shintani's formula give you a formula for the L function. That is, if you the whole point of Shintani's method is kind of you're taking a fundamental domain for the units. So if you mod out by the units again, then all you're saying is that you're getting the L function. So that's kind of the first fact, is just understanding that Shintani's formula, if you mod out by the units, gives you the L function, is just saying that the analytic element that you've written here, is the L function. Okay, so that's the first step. And the second step is, why do I get ones here? Okay, so if you project onto each core component here, the fact that you get the VP, if you only looked at P instead of all the places above SP, that's kind of just how the construction works. It's sort of component by component. Now the question is, why do I get ones here? You kind of need to, if Gross, you're going to have some consistency in Gross's conjecture. So, but why does it work? It works because of the trivial zero at P, that P splits completely. Somehow, the fact that when you P splits completely means that when you project onto some other component means that you're going to get a 1 there. And this is most easily seen in the case where, P is inert. It's generated by a rational prime P. The point is that multiplication by a rational prime preserves these simplicial cones. And so you're kind of taking a linear combination of two of these, but they're actually the same because multiplication by P preserves that cone. So that's kind of sort of some conceptual reason as to why this congruence holds. Okay, and then once you get that, what do we conclude from that? That means that if you were to prove that Gross's conjecture holds, that is, if you were to prove this congruence, well, then I already have this congruence. This is a purely analytic thing, which I've just kind of explained with a little bit of hand waving. Then I get a congruence between these two, right? Then I get that UP1111 is equivalent to VP1111, which is to say that UP is equivalent to VP. But again, you're still working, this all holds only in the quotient, right? So this holds in the quotient by this group of units, the group of P units. So in other words, it means that Gross's conjecture holds in the subgroup of FP, the quotient, okay, of by this thing I call DH. That is, it's the elements of FP star such that X111111 is in the topological closure of the group of P units. Okay, so this is kind of, this conclusion just follows directly from what's on the slide already. It's just restating what's on the slide. Okay, and then the punchline is, now we're going to sort of change the set S in such a way that UP and VP don't change too much, and I still get the same congruence, except I want to make this thing that I'm modding out, this thing that I'm modding out by, this DHS, smaller and smaller. And if I can make that, go off to, as small as I want, make it trivial, essentially, then I've shown actually an equality for UP and VP. So that's the kind of punchline. So what happens if you adjoin a prime Q to S? What happens? Well, then just by the formalism, if you look at the definition of Stark units, then UP gets replaced by UP divided by sigma Q of UP, where sigma Q is the Frobenius at Q. So if you choose a clever prime Q such that its Frobenius is complex conjugation, well, we know complex conjugation acts on these units as inversion. These all have complex absolute value 1. So its complex conjugate is its inverse. So U divided by sigma of U is then U divided by U inverse, which is U squared. So if you choose a clever prime P such that its complex conjugation, its Frobenius is a complex conjugation, then you just squared your unit. And for such a Q, you can also show that on the V side, the purely analytic side, you just square the V. Okay, so the conclusion is if P is not 2, then if you're looking p-adically, right, if you sort of tensor with QP, the pro P part, then you can get rid of this 2. You can take square roots, where you're tensoring with, right, the kernel multiplication of squaring is plus minus 1, and that goes away when you tensor with QP if P is not 2. Then if we join a bunch of primes to S, whose Frobeni are all complex conjugation, then I get sort of U to the 2 to the K is congruent to V to the 2 to the K, and you can get rid of that 2 to the K. So you get that U is congruent to V in the pro P part of FP star modulo D of H S prime. So now I'm allowing myself to change my set S and make the, possibly make D of HS prime smaller and smaller by choosing these primes cleverly. And I'm getting a congruence for the original units with the original S. Okay, so that's sort of the idea. And this idea, I should mention this is, called horizontal Iwasawa theory. This idea of expanding your sets S and and kind of getting, the quotient that arises in class field theory, making that smaller and smaller. This is a very powerful technique that was introduced by Wiles and was used to great effect by Taylor and Wiles in the proof of Fermat's last theorem. So this is this kind of idea has, very rich history. And I should say that this kind of idea was pointed out to me by Taylor back when I was a postdoc at Harvard, and I gave a seminar talk on my conjecture. He kind of suggested, he just made a one-sentence comment. He said, "What happens if you expand S?" And that kind of led to this argument. So, and so, yeah, you can make D of H S prime arbitrarily small. So under some conditions, so we need some conditions. So suppose that F adjoint mu P infinity is contained in H prime, the maximal totally real subfield of H. Then for any positive integer M, you can choose these auxiliary primes, as I said, such that the Frobenius complex conjugation and that D of H S prime is as small as you want, so is contained in 1 plus P to the M. Okay, so it's sort of 1 mod P to the M. And if you do this for every M, then you get that UP is congruent to VP modulo P to the M. If you do that for every M, then you have that they're actually congruent. Okay, and I'll just sketch the proof of this. And by the way, I want to say that this condition is ensured by my condition that P doesn't ramify in F. So that's why, once you throw in the assumption that P splits completely in H together with P doesn't ramify in F, that this makes this automatically hold. So that's why that condition was in the earlier version of the theorem that I gave. Okay, so how do I sketch this? Well, how do I prove this? So you choose these primes such that the norms are congruent to 1 modulo P to the M, and such that for each unit, epsilon is not congruent to 1 mod P to the M. Such that for each unit that's not congruent to 1 mod P to the M, there exists a QI such that epsilon is not congruent to 1 mod QI. So the point is that this unit group, right, that you're modding out by, this D of H S prime, this was basically units congruent to 1 modulo everything in S prime. So if you enforce your condition that every unit that you're worried about is not congruent to 1 modulo Q prime, then you have kind of gotten rid of that unit. Okay, and so you kind of, the thing that you're modding out by is getting smaller and smaller. Anyways, these are all Frobenius conditions, and by the assumptions, that's why you need sort of these assumptions, they're mutually exclusive. Okay, so there's kind of details on this in my paper in Duke Math Journal. So the details of this proof are given. But long story short, it's basically just the Chebyshев density theorem kind of applied correctly. All right, so putting everything that I've said together, what you get is that the conclusion is that Gross's theorem, Gross's conjecture, implies the refined conjecture. That is, if P is not equal to 2 and P is unramified in F, that implies all the assumptions of the previous construction. Then Gross-Tauer Field's conjecture implies that UP is congruent to VP as long as you mod out by the roots of unity. Okay, so that's the non-P part of FP star is exactly kind of in the roots of unity. Or I should say in the topological closure of FP star, the p-adic completion of FP star as kind of the image of FP star mapping to the p-adic completion. The kernel of that is the group of roots of unity. That's what I'm trying to say. So that's kind of where you lose some information. Okay, so then you're still left with proving Gross's conjecture. So I kind of haven't said much about that. So how do you prove Gross's conjecture? So the way that we do it is motivated by Greenberg and Stevens. So the Greenberg-Stevens L invariant, for those that have studied the proof of Greenberg-Stevens, the conjecture of Maser-Tate-Teitelbaum, the Greenberg-Stevens L invariant is the ratio between the derivative of the p-adic L function and the classical L function. Now, unfortunately, we can't take ratios in our work because everything is integral. So what we have to do is we have to create a ring. We create a ring in which there's a formal stand-in L for this ratio, right? And what is the derivative of the p-adic L function? Well, I mentioned that earlier. That's the role that is played by the image of this theta, the STICKELBERGER element, in I mod I squared. So that's kind of what I'm denoting theta L here. So this is okay, so because for notational reasons, I haven't put all the adornments here. This is theta SP comma t of L over F. Okay, so this is the thing that we're looking at in I mod I squared. Okay, and what you really want to take is somehow the ratio between this theta and the L function downstairs, that is the sort of simpler theta sub st of H over F. Okay, and that's what I'm just denoting theta H. So I'm kind of simplifying my notation so it doesn't get too heavy. And what you do is you just make a form. Oh, this is a typo here. I'm throwing in. I have to put this is very important. I'm throwing in a variable x. So this is just a polynomial ring in L. So I take ZP bracket G and then I throw in a formal variable L, and then I make L. I force L to be a ratio between the derivative of the periodic L function and the classical L function. So I mod out by L theta H minus theta L. Okay, and now for this to all make sense, I mean, you only want to consider I mod I squared, so you have to mod out by a bunch of other stuff, I squared, L squared, and IL for this to kind of make sense. Okay, and then that's a nice ring that you can work in which you have a formal algebraic version of the Greenberg-Stevens L invariant. Okay, and then the construction kind of with modular forms is kind of parallel to the construction that Dorman and Pollock and I used to prove the Brumer-Stark conjecture, which was based on the Greenberg-Stevens method of studying this L invariant, right? So in that work, we kind of use the honest ratio here. Okay, sorry. So I know I'm a little bit over. I'm almost done. So what we do is we defined a generalization of this Ritter-Weiss module that I described. I didn't really define last time, but I told you some of its properties. Nabla L, which is a module over the ring RL. And it's constructed in such a way, it's kind of formally, that its fitting ideal is generated by the thing that Gross wants to be 0 in I mod I squared. So Gross's conjecture is that this is 0 in I mod I squared. Okay, and by the construction of this Nabla L, it kind of sees these Brumer-Stark units. The construction is that the fitting ideal is generated by this thing that you want to be 0. Okay, and kind of the construction of this Nabla L is inspired by work of Kurihara, Burns, and Sano. Okay. All right, and so then you prove the result by proving two separate theorems. So first is that the fitting ideal of this Nabla L is 0. Okay, so that's what you wanted. You wanted to show that, okay, the fitting ideal you can see by construction is the thing that you want to be 0. So you got to actually prove that fitting ideal is 0. And how do you do that? You do that by Ribot's method. Okay, so you give a cohomological interpretation of maps from Nabla L to some module n. And then once you have that, you construct the cohomology class that you need to with this cohomological interpretation such that its fitting ideal is 0. And that's sort of Ribot's method, a beefed up version of what I described in a little bit more detail in the last lecture. And the second is that, well, you're cheating a little bit because you've shown now that the element that you want to be 0, which is some element of I, you want to show that it's actually an I squared. But for that, you need to know that the canonical map from I mod I squared into this ring where this element lives is actually injective. That's actually important and non-trivial. And the key fact is that your theta L lives in sort of a product of relative augmentation ideals. The kernels of this GV is the decomposition group at V. And this fact, this is some version of kind of Gross's conjecture of Gross, this inclusion here. And that actually follows from our previous work on Brumer-Stark that I described yesterday, kind of not the fancy version I have above, but just the version that I described yesterday. You can show that since theta L generates the fitting ideal of the usual Nabla L, the usual Ritter-Weiss module, you can show that this generator of the fitting ideal has to live in this kernel. Okay, so that's a kind of whirlwind summary of the proof, and hopefully there'll be some expansion of this in the future lectures. And I apologize for going over. Thank you very much.
So let's thank Samit for his talk. Are there any questions?
Hello. Yeah. So in your previous proof, like you have this away from 2 part, right? So that doesn't like create any trouble for creating these units, let's say, like for the construction of explicit class field theory?
Yeah, I mean, yeah, so absolutely. We still don't have anything, yeah, the stuff at 2. So yeah, I mean, not really. I mean, there's several things to say there. I mean, the easiest way for me to get out it is we know how to do the 2-part for cyclic extensions. And, you know, to generate an abelian extension, it suffices to generate the cyclic extensions. So that's kind of the easiest way out. But even with, you know, in the general case, so somehow if you raise your thing to a 2 power, then you will get the you know, the right element. So yeah, there is some ambiguity there. I mean, probably the simplest way to handle it is for us to just prove the 2-part, and so we're working on that.
Okay.
I expect that we'll have that soon, but I can't promise anything. But yeah, certainly for cyclic extensions, we do have it already, and so, you know, for a generation of abelian extensions, that should be sufficient. Yeah.
And also, like for this splitting polynomials, what you showed in some examples, right? There are some symmetries in the polynomial coefficients. I mean, is there some theoretical reasoning for this? Like,
yes, because they have complex absolute value 1. So kind of the inverse u will be, you know, u inverse will be a root of the minimal polynomial of u. So the coefficients will be symmetrical. It'll be a palindromic polynomial. So.
okay. Okay, thanks.
Yeah, so that's required by the, you know, the construction of the units.
Any more questions? So I have a non-math questions. Will your lecture notes be available online after today?
If you want them to be, I can email them to someone.
Yeah, you can email them to the organizers. I think they can put it on the web page, I suppose. That's probably
okay. Okay. Yeah, it'll take me a little bit of time to, yeah, but I can do that.
That will be great. Thanks. Any other questions, comments, anything? Okay. Looks like there are no other questions. So let's thank Samit again.
So there's a question in the chat about, is it possible to relax the condition that P splits in F? I don't think so, actually. I mean, the Brumer-Stark unit kind of lives in the maximal subfield of H in which P splits completely. So I think that's actually an important condition in Stark's conjectures.
I guess, I hope there are no more questions in the chat because I cannot see.
Yeah, I don't see anything else yet.
All right, so we have a short break now and we'll resume at 5:30.